Okay, and one very important thing about these electromagnetic waves is that electromagnetic waves are transverse waves. Okay, if you go back to spring semester, actually we learned there are two different types of waves. So when this is the direction of the wave traveling, and wave means something is oscillating. So therefore, if the oscillation or displacement is along this direction, we call it longitudinal waves, right? And then if something is oscillating like that, we call it transverse waves. The example of the longitudinal wave was the sound wave, right? And then now we see that the electromagnetic waves are actually transverse waves. Okay, just like here in this example or in this figure, this wave is traveling along this direction, which is x. And then here we see that the electric field is pointed along this direction, always up or down, but is always along the y-axis, and magnetic field is always along the z-axis, right, which is perpendicular to x. So therefore in this case this oscillation is always transverse. So therefore electromagnetic waves are transverse waves. Okay, and now let's think about this electric field, and then their oscillation always happens within a certain plane like this, right? So we call it plane of oscillation, and it makes them plane polarized. Okay, so now let's assume that we are observing this from the direction along the x, and then okay, now you will see the electric fields going oscillating this way. So here this is y and this is z. Okay, and then you are looking down along minus x direction, and then since the electric field is oscillating back and forth, up, down, now you can use the double arrow like this to represent their plane polarization. Okay, but then important thing is that when you observe light from the sun or observe light from the lamp, actually there is no particular reason why electric field will be along the y-axis, right? So in fact typically it can be any direction, for example like this. So it is all around this 360 degree direction. We call it randomly polarized or unpolarized. Okay, so it's distributed like that, and which is in fact a summation of all the small arrows going around like that. Okay, and in fact these arrows covering 360 degrees, they can be represented only by using two arrows. Actually an arrow going along the y-axis like this, and then another arrow going along the z-axis like that. Okay, and then let me explain it. Suppose now you have one polarized light like this one. Okay, this is tilted, but still it is only within a certain plane. So therefore it is polarized, but then this component of the polarization can be divided into two. One small component parallel to the y-axis, and another component, a longer component along the z-axis. And when you combine these two, you can actually make this original one. So which means that whatever direction you choose, you can all decompose them into two components along y and also along z. Okay, so that is the one important thing. Okay, so this sentence again saying that a collection of unpolarized waves can be divided into the superposition of two orthogonally polarized waves, which means in this case orthogonal means 90 degrees, so along y and along z. Okay, and if the oscillation is neither completely random or is not also parallel to a single axis, and it is called partially polarized, which means that completely random means that it's uniformly distributed around this 360 degrees, but there may be certain situations and you have some arrows along this direction or that, but not much along the other. Anything like this is called a partially polarized. Okay. Okay, then how do we make unpolarized light or randomly polarized light into plain polarized light? We do it by using a device called a polarizer. Okay, and in fact, okay, let me mention one thing. Previously we learned that the electric field and magnetic field are perpendicular to each other, so therefore which means that when the electric field is this way, then magnetic field will be that way. But when we talk about polarization, now let's talk about only the electric fields, because magnetic field actually is a little bit difficult to explain, but magnetic field does not really interact with matter. So whenever you use polarizer or you want to make a reflection or refraction, that is all about electric fields. So so now let's forget about magnetic field in when you deal with electromagnetic waves. Okay, anyway, so now suppose you have completely unpolarized light, and then we just said that each component of this light can be divided into two orthogonal waves, which means that fully unpolarized light can be represented by two orthogonal vectors or double arrows like that, one component going vertical and the other component going horizontal. Okay, and then you use a device called the polarizer, which actually looks like this. It allows only the light having a vertical electric field to pass, which means that if the electric field is oscillating sideways or horizontally, it's not going to pass. Okay, so as you can see here, only the electric field components vertical have passed the polarizer. So this is how this polarizer works. And actually, as a result, as you can see, this component disappeared while this component is still there. So if the original intensity of the unpolarized light was I0, then after passing this polarizer, intensity would have been reduced by half. So it's half of I0, because one of these unpolarized light have been disappeared. Okay, and then next one, and then we can actually try to use another polarizer to a polarized light. Then we have a choice of the angle. Now suppose this arrow here is the same arrow as this guy, which means that now we are going to use another polarizer at an angle theta with respect to this polarized light. Then what will be the intensity of the light after passing this second polarizer? Now actually, you know, this is about electric fields, so only the electric field component parallel to this polarizer, actually along the y-axis, will pass, which means that only the cosine component of the electric field will pass. And then we know that the intensity is always square of the amplitude. So therefore, the total intensity will be the original intensity multiplied by cosine square, because always remember the intensity is the square of the amplitude. So therefore, this electric field is the amplitude. If you take the square, then you get cosine square. So therefore, after passing one polarizer which is at an angle theta with respect to the plane polarized light, then after passing this polarizer, intensity will be reduced by cosine square theta. Okay. Alright, like I said in the beginning, this online lecture was not very long, even when we have two chapters together, right? Okay, so let's make a summary of this lecture. So in this lecture, you have learned 4 Maxwell's equations. The first one, Gauss law for electricity, and second, Gauss law for magnetic fields, and third, the Faraday's law of induction, and lastly, the Ampere-Maxwell's law of induction. Okay, and then we learned what is the speed of these traveling electromagnetic waves when we try to use Maxwell's equations. and from there we learned that these electromagnetic waves are in fact light waves, which was proposed of course by James Maxwell. And we also learned that lights are transverse waves, so therefore we learned how they are polarized and also how polarizers work. Okay. And in the next lecture, we will study more about the wave properties of light. So it will again be very closely related to the waves that we learned in the spring semester. But there, in spring semester, we focused more on sound waves. But here we will focus more on light waves. Okay. So I will see you on Thursday in the classroom. Okay. And then goodbye.